Hello, everyone. My name is Baldur Steingrímsson, and I'm going to provide you with insight into Imagars' work on machine learning and data analytics for accelerating design and manufacturing of alloys and propellants. We are presently working on an STTR Phase 1 project with the Air Force on application of machine learning and data analytics to propellant design. So I want to, we are collaborating with Oregon State University on that, but I want to give you kind of general insight into our company, in particular as it pertains to the Air Force project. So Imagars is a small company located in Portland, Oregon. We've been around, I guess it's close to a decade. We've worked on actually we started out with an SBIR Phase 1, Phase 2, and Phase 2A project with the National Science Foundation related to engineering design. We've developed an ecosystem for design assessment and verification. And we are, how to say, gradually building up the company. My co-founder will be leaving his present employer probably within a year or so and joining Imagars full time. But we've been around, we got patents, and how to say, we believe in super lean operation. So in regards to our patents and the background, here you see one patent application related to application of machine learning to accelerate alloy design. But in addition to this, we have two patents already granted related to, engineering design. Furthermore, I guess I'm listed as a first author of a textbook chapter, which in a textbook that Springer will be publishing later this year. It's a textbook on high entropy materials, and there are some very preeminent authorities like the godfathers of high entropy alloys, Professor Ye and Professor Brian Cantor, that are also contributing to that textbook. So it's a highly esteemed company, and I'm honored and privileged to be, invited to contribute a textbook chapter there. And then there is more. We have a number of conference presentations and also working on journal papers, primarily with Professor Peter Leo from University of Tennessee. But in terms of the machine learning, we are, how to say, building up a database, and we already have a database for high entropy alloys and how to say, conventional alloys, super alloys. So we take a structured approach and systematically build up, harvest the literature and build up the database. And then we've adopted a similar practice for the propellants, and we clearly define the inputs, the outputs, and systematically build up the database. And the end products envisioned relate to some type of joint optimization schemes, especially for the propellants and for designing or alloy design. But in addition to that, we have additional software products kind of on the drawing board, and we have been exploring applications of machine learning to accurate prediction of fatigue life of alloys, and also we have, devised machine learning framework for predicting AM process parameters, and actually also for reinforcement learning for real-time closed loop in situ AM process, quality control. And how to say, there probably will be upcoming journal papers that expand on this, but just briefly, we believe in, how to say, combining some type of machine learning, maybe off the shelf, with physics-based modeling. And in case of the Air Force project and the design of the propellants, we think the relevant physics-based modeling may involve some type of molecular dynamics. And in general, we want to build know-how through journal publications and know-how and credibility. And then we want to protect the uniqueness of our work through patent applications. And as I noted, we already have patents granted, and there will be more to come. So that's just a brief introduction to our work related to machine learning, data analytics, and so on. So I want to thank you for your attention. Thank you for listening, and goodbye now. Thank you.